the last speaker of this morning before the coffee break is Mahsa Yousefi from the University of Trieste, and she's going to present combined first and second order directions in deep neural network training.
Thank you, Marta. Hello, everyone. First of all, I highly appreciate that the organizer of this conference. I'm Mahsa Yousefi from University of Trieste. I'm gonna talk about combined first and second order directions in deep neural network. I joined work with my advisor, Angela Martinez, Marco Viola, and Daniela Di Serafan. As you know, a few weeks ago, unfortunately, we missed Professor Daniela Di Serafan. This talk is dedicated totally to Daniela, to may her soul rest in perfect peace. So, let's talk a little bit about the broad generality of my talk. The generality is optimization algorithm in deep learning. But why deep learning? As you know better than me, deep learning is a machine learning technique that has breakthrough in different fields of studies, such as image recognition, text translation, speech processing, image universe problem, and many other fields of study. I'm going to talk about image recognition. So, to train deep neural networks in large scale problems, we have to solve a large scale and unconstrained optimization problem in deep learning. So this problem is non-convex and nonlinear. To solve this problem by traditional deterministic optimization algorithm, whether first order or second order method, is possible, but it's difficult to use deterministic for solving such a problem. Our goal in this talk is that we introduce a new stochastic algorithm combining first order and second order information. So let's see what is this strategy, combined strategy using first order and second order search direction. The idea is simple. Temporarily, consider we have minimization, something like this, whose objective function is is differentiable, and whose Hessian is this, and gradient vector is this. Okay. For convex optimization problem, consider this objective function is convex function. If you are going to use a second order method, such as Newton, an exact Newton or Quasi-Newton method for solving this problem, we know that under some standard assumption, these methods are locally convergent. So, in further step in non-convex optimization or even in convex, we cannot talk about global convergence without these standard assumption. Holding global convergence is hard. So one possibility for having global convergence is using line search. In line search strategy, this approach requires a second order direction, such as pk, that satisfies angle condition. What's the meaning of this angle condition? That means the cosine, the angle between our second order direction and the anti-gradient must be far from zero. That means we are not interested to have a direction which is orthogonal with our anti-gradient. Moreover, we need to compute a step length such as alpha k, ensuring our new condition. That means we are interested to have a sufficient decrease in our function value. Okay? So, up to now we have an optimization, minimization in deterministic case, whether in convex or non-convex setting. We are going to use line search step to make a convergence, global convergence. But what's the problem? The problem is here. In some cases, the angle condition doesn't hold. What's the meaning of that? Consider convex case. If you have the minimum or maximum value of the eigenvalue of your Hessian matrix, you can prove that the cosine of pk and antigradient is positive always. This is exactly our cosine condition. But what's the problem? The problem is that if the condition number of your Hessian matrix is very large, in that case cosine is close to 0. That means pk is exactly orthogonal with our antigradient. We are not interested in such a second order direction. Moreover, in non-convex case, so it's you may not have a descent direction. If you have ascent direction, you cannot prove or you cannot make hold the RMU condition. So the solution is this. If the cosine of pk and minus gradient is less than an epsilon, which is larger than far from 0, if angle condition doesn't hold, we can find a beta, a parameter beta, such that for this beta, we can have a combination direction by using this second order direction and our antigradient. For this combined direction, we can prove that the cosine condition holds. This idea, which is steepest descent globalized method, in 2000, first time in this paper in year 2000 proved, and then Daniela Di Serafano, Marco Viola, and Doraldo extended to this formula, which is they add this multiple here and prove that by adding this multiple we can have a better result. And they proved the theorem, and they could show the optimal value of this beta. So I remove the theorem just to tell you the generality of the combined strategy is this. Okay, what's our concern? Our concern is that to answer these two questions, is it possible to apply this strategy for stochastic optimization in deep learning applications? I answer now, yes, it's possible. At least our experiments show this. The second question is that, how can we choose the first and second order direction in a stochastic case? I will answer to this question in next few slides. Okay. Before that, I'm going to talk a little bit about this algorithm, stochastic, a limited memory SR1 in trust region, which is the foundation of our algorithm. Then I will switch to our new algorithm. Okay, so let's see what is deep learning and training deep learning. As I mentioned at the beginning, we are interested to solve an image classification problem. Okay, so it's clear that we have a supervised learning problem. In supervised learning problem, we are going to solve this minimization problem, which is a summation of n loss corresponding of n single error corresponding with our input data and its target. And here, y hat is the output of our network. So something that we are interested in is that to minimize the error between our predicted label and true label corresponding with this input data, which is an image. Okay, so the problem for this minimization problem is that in practice, this problem is highly nonlinear and might be non-convex. And the other problem is that n, the number of samples are very large, and also the number of parameters is very large. In practice, in a stochastic optimization problem, at each iteration, we can choose a subsample function with respect to a random subsample, something like jk, at each iteration. So this subsample function is evaluated per each iteration. The formula is that, as you can see, instead of n samples at each iteration, it's sufficient you choose a limited number of your data set. That's it. So, what was that algorithm that I mentioned in previous slides? Okay, so a generic second-order based algorithm to solve this supervised learning problem is a stochastic limited memory SR1 in trust region. The idea is simple. You can reduce your minimization problem into a quadratic optimization with this formula, a quadratic function. Here, bk is our LSR1 Hessian approximation with this formula. In this formula, yk and sk can be obtained by this form, which is the differences of every two successive parameter and their corresponding gradient. Okay? How we can update our parameter? We can update in this way, in trust region. We have to compute our trust region reduction ratio that shows us how much our model behaves similarly as our function, original function. If they behave similarly, we accept our trial point. We accept this computed direction in this restriction, which is usually a ball with radius delta. We accept this pk and update our parameter. Otherwise, we have to continue with the previous parameter. That's it. How we can solve this problem? There is a very nice direct method for solving this minimization, this trust region optimization. You can find in this reference. It's very nice algorithm. It's not an iterative method. It's very fast. It's direct method. Anyway, I will skip these slides and go to our new algorithm. Okay, what's our new algorithm? Still remains two questions for answer. What's the second order direction and what's the first order direction in the combined strategy? The first answer is that in our algorithm, using combined strategy, the second order direction is exactly something that I mentioned now. It's the solution of our quadratic optimization that comes from trust region problem. So, by having this second order direction that comes from solving quadratic minimization with LSR1 Hessian approximation, then in the next step, we can compute our first order direction. In the next slide, I will talk about the answer of this question, that what is first order direction. Okay, by these two directions, we can compute the cosine condition. If the cosine condition doesn't hold, we can apply the combined strategy. We can find a beta, and for this beta, we can compute this combined direction. For this combined direction, for sure the cosine or angle condition holds. Next step is optional. You can apply a step length alpha backtracking approach to make a sufficient decrease in your function. Apart of that, In the next step, we can compute the trial point by using this combined direction and this computed alpha. Then we have to compute trust region ratio. Then we can adjust the trust region radius by the value of this trust region ratio. If it is okay, we can enlarge this value. Otherwise, we can reduce it. Okay, in the last step, we can accept or reject our trial point. If the value of rho is larger than eta, which is 10 to the power minus 4 in our case, we can accept. Otherwise, we reject. This is the steps or our algorithm that we call it stochastic combined LSR1 in trust region framework. Okay, so the last question. How to compute the first order search direction? Our expectation is this. We would like this vector vk to reproduce the behavior of our full gradient. In practice, it's hard because we are working in a stochastic setting. So here we consider two class of options. The first option is moving gradient average. In moving gradient average, at each iteration, you compute your current subsample gradient and you can add it to your latest average. So it's simple. In the next class, which is the variance radius gradient approach, here I listed a couple of so-called well-known variance reduction methods, such as SVRG, SARA, and SAGA. I don't want to go in details, just tell you the generality of them to tell you it makes sense using these approaches to take a vector which is follow the behavior of our full gradient, because they all try to reduce the noise of the gradient. Okay, in SVRG, at each epoch, you have to compute a full gradient, and then at each iteration, you have to modify this full information by your local information of your gradient. In that case, you can reduce the noise of your gradient. Okay, so we can select this V vector as our vector that we needed. The same happens for SARA. At each epoch, again, you have to compute a full gradient, and then at each iteration, you can modify this information by your local information. For SAGA, the mechanism is a little bit different, but the goal is the same. At each epoch, at the beginning of your algorithm, you compute a full gradient, only one full gradient. And then you store every single gradient on a storage matrix that we call it Jacobian, and then keep this matrix for all the training process. Because at each iteration of your training process, you have to modify the information that you store the column of the Jacobian. This is the mechanism of the SAGA. Okay, so these two classes are our options for choosing VK. So let's see what's happened in practice, empirical evaluation. We have followed two goals. First goal is that we were interested in to compare our algorithm with a well-known and widely used algorithm, which is Adam. But you know, Adam is famous because at each iteration it's very low cost, but in practice you have to tune it. It's important to tune your hyperparameter, which is learning rate. Here you can see we have three figures, each of which shows testing accuracy corresponding a specific batch size. Okay, so for different learning rate, we have three different testing accuracy. Finally, we find the optimal obtained alpha k for each of these experiments. Okay, so now we are going to compare our algorithm with this tuned Adam. In a stochastic combined LSR1 truss region, using moving gradient average, here you have 3 figures that if you follow the purple curve and the red curve that compare the testing accuracy of Adam, tuned Adam, and our algorithm, you can see the behavior are more or less the same. But with this difference, in our algorithm, there is no tuning, everything is automatically, and with less overfitting. So the same happened when we check with SVRG for choosing a vector VK. Again, everything is comparable. We have obtained the same behavior for the next option, which is Sara. Here at the beginning, our algorithm is not good, but at the end, outperform Tune Adam. And the last approach, which is Saga, still all are almost the same. So when we review this strategy, we can see, okay, variance reduction approach and moving average produce the same and comparable result with Tune Adam. So it's better we use the moving average gradient, which makes nothing. The cost is nothing in that case. You need only one storage vector. But in Sara, Saga, and the SVRG, at each iteration you have to compute a full gradient or you need a storage matrix that costs a lot. So it makes sense that you use a moving average for choosing the vector VK. So finally, we were interested in to see the effect of L2 regularization in this approach, our algorithm with PK, which is LSR1 direction, and moving gradient average. Here, I included different values for lambda, which is L2 regularization parameter. In all of them, they produce the same testing accuracy. That means our method is not sensitive to the hyperparameter L2 regularization parameter, unlike Tune Adam. So, but using L2 regularization is helpful because here without regularization, testing accuracy is here, but with L2 regularization, testing accuracy for different value of L2 regularization parameter is here. When we compare one of these with Tune Adam, as you can see here, our algorithm is very much better than Tune Adam. That's it. So for conclusion, I would say we have introduced a stochastic optimization algorithm that combines both first order and second order search direction to train deep neural networks, in our case, image classification task, by using ResNet model, ResNet 20, which is a very deep model. We have analyzed different strategies to compute first order search direction, while the second order search direction for all the cases where LSR1 updates. We have compared our algorithm with the state-of-the-art Tune Adam optimizer. As you saw, our algorithm without tuning, with less overfitting, provides comparable testing accuracy than Tune Adam. Our algorithm is not sensitive to L2 regularization parameter if you use the regularization parameter. With the L2 regularization, our algorithm outperforms Tune Adam. That's it. I highly appreciate for your attention to my talk. If there is any question.
Thanks for the nice talk. Are there any questions? I have a couple of.
I was wondering, did you observe any difference in behavior when you change the batch size, like comparing the two algorithms, Adam and yours?
In Adam, yes, as you.
Because yeah, it looked like in the yeah, that with the smaller batch size,
Yes,
it worked even better than Adam.
For different batch size, in Adam there is a little bit differences between different batch size, but when you use a smallest batch size, the oscillation in Adam is more than when you increase the batch size. But the accuracy of tune Adam, for all the batch size are almost 70%. Almost 70%, but a little bit change. It's not so remarkable that I say when I increase it, it's for instance 80%. No, in the range of 70% to 75%, not more.
Okay.
Something similar concerning the batch size, and if I understood well, you always use a sort of approximation of the full gradient for the first order in your method. Okay, I think that this is actually a different way of thinking the problem from people that comes from classic machine learning to deep learning. Because actually, in classic machine learning, you use mini batches because the full gradient is expensive.
Yes.
Actually, in deep learning, the full gradient is not expensive unless for memory reason when you are working with images. So actually, I can compute the full gradient in almost the same time of a mini batch. And
Yes.
on the other hand, in deep learning, theoretically prefer the completely stochastic gradient in the sense of mini batches of one sample, because theoretically they have more generalization ability, but you have only to wait much more for the training. So in deep learning, theoretically you want a full stochastic method, but you must use mini batches bigger because you have not enough time to train the network. So maybe you can try to not use the a full gradient approximation, but a classic gradient computed with respect to mini batches.
Yes, here we didn't use full gradient.
No, but an approximation of it.
Yes, we can approximation of.
And you tend to stack to
No.
something.
You see here we are using the subsample gradient. Always we are working with subsample gradient. For instance, here, if you follow the SVRG, at the beginning, yes, you are computing a full gradient. But in the middle, in your inner loop, you are going to compute a mini batch gradient at each iteration. It's not a stochastic with respect to one sample. It's a gradient, subsample gradient with respect to a mini batch.
Yeah, okay.
At each iteration, you are computing this one.
Any other question? So if not, let's thank the speaker again.